Hi all, welcome to part 12 of the video lecture on module 3, combinational circuits. Now, so we are continuing our discussion on decoders, right? So what is a decoder? We already seen the previous part, hope you remember. So what it is done? So given the encoded form, so decoding and encoding are two different operations, right? So from the original form you can give it some code, right? Some binary code or some other type of coding you can give. So that is the process happening in encoding, and that we are going to see next. And now we will see, suppose I have the coded information with me, how can I retrieve the original information? So that is the idea. So that is what is done by the decoder, right? So typically this decoder will be having some so the coded information will be, say, some n bit code I am having, right? So this n bit, it will be decoding to some any of this 2 power n combination, if all the 2 power n combinations are valid, otherwise accordingly, right? So so this is something, the maximum size of a typical decoder. Now if you want to construct a suppose the original code, maybe the binary you can imagine, or something else also. So binary type of encoding and decoding is what we've seen so far. So let's take that same example, and your motivation is like us, you have to construct something called a 4 by. So tell me, if 4 by, then what is the next parameter here? By default it will be 16, right? So what is this 16? It is 2 power 4. Okay, so I want a 4 by 16 decoder. So that is my requirement, right? So what is happening is, for the decoder I am giving 4 inputs, say x, y, z. Let the 4 inputs be x, y, z. Input 1, 2, 3, 4, right? So there are 4 inputs to the decoder. Say let the most significant bit be W. So this is my MSB, then X, Y, Z. So these are all the inputs to the decoder. Now this decoder is like a 4 by 16 decoder I am having. And what about its output? Its output will be like some 16 outputs will be coming, right? So I am denoting by a single line, but actually there are 16 different lines, and it can vary from the decoder output to 0 to some decoder output 15. So 0 to 15 we have 16 different output line. Now how it will be working? So just a 3 by 8 decoder, you know, right? So you can refer it, or let me show you. So this is the typical 3 by 8 decoder we've seen, right? So here the 3 inputs are coming. Now in addition to that we have one more input, 4 inputs. So there will be some 16 rows in this truth table, and D0 to D15 lines will be there. So at any times when you are giving the input like 0, 0, 0, 0, 4, 0, only D0 will be activated because it corresponds to D0, right? And all others will be 0, deactivated. D0 output line. Similarly, when you give like some 4, 1, 1, 1, 1, 1, only D15 will be activated and all others will be deactivated. So this is the typical implementation of decoder with the enable input, hope you remember. And so that the decoder will be enabled only when you are giving a 1 to the enable input. So this kind of a construction we already having. So this is the implementation of a, not this one. Yeah, something like this, 3 to 8 line decoder. So if you want to add enable, you can add like that, something I explained in the last video. So this is a typical implementation of a 3 to 8 decoder, and similar way you can implement 4 to 16 decoder also, but it will be very complex, right? So this here you are having some 8 and get instead in 4 to 16 decoder, same way you will be using some 16 AND gates. So like that also you can design, but what we are going to see is, can I make use of this chip? Suppose I already implemented this 3 to 8 decoder, so it is available as a single chip for me. Can I make use of that chip, maybe 1 or 2 chip, and can I construct that 4 by 16 decoder? So that is the concept we are discussing here in part 12. So it is just like instead of making the normal implementation, I am trying to implement the 4 by 16 decoder with the help of 3 by 8 decoder, which is already implemented. So take two different 3 by 8 decoder chips, so just like what is shown in the figure, with the enable input. So now we have the application of enable. So this kind of an implementation will work only if the decoder circuit is allowing you to give an enable input. Okay, that kind of circuit only you can make use of constructing bigger size decoder. So this you can generalize to any level also. So just understand the construction. So what is happening? So 3 to 8 decoder with the enable input is needed. Okay, so keep that in mind. So you take 3 to 8 decoder with the enable input like this. Now when you are writing this 4-bit in binary, so let me write like say W X Y Z. So it is something like a 0 0 0 0, right? So some 16 combination I am having, and let me tell you the first so the first half of the combination, it will start with the 0, and this 3-bit will vary from 0 0 0 to 1 1 1 1. So this is the first half combination. So whenever this is the case, this D0 will be activated and all others will be deactivated. Now in this case, this D1 will be activated and all others will be deactivated, like that, right? So etc. So in this eighth case, what is this? This is D7, right? So only this all others will be 0, only this D7 will be activated. So this is the type of construction we are having. Now for the second half of the combination, you can see they are all starting with the immediate next combination is 1 0 0 0. So that is your D8, right? So correspondingly I want to activate the D8 pin. All others can be 0 0 0, like that. So it is going like this, right, etc. And the last combination, you can see. So the observation is like the exactly this 0 to 7, they are starting with the 0. The half of the combination, and the remaining half is starting with the 1. So 1 1 1, only this D15 will be activated and all others will be deactivated. So this kind of a construction is what we are having. And what I am doing is this output line that is already there in your mind. I am removing this output line. Okay, let me focus only on the input. Okay, so this is the observation I want. So the second half is starting with the and next one is like this, and you can see the most significant bit you fix as 1, and the remaining 3 bit will vary from 0 0 0 to 1 1 1. So like that you can write the second half set of binary. So these are all the possible inputs I can get, right? So what I am doing is a least significant 3 bits. See, the least significant 3 bits X, Y, Z, I am applying to both the decoder, right? So the first decoder will be taking this X, Y, Z, and the second decoder will also take this X, Y, Z as the input, because we have the 3/8 decoder, the input is some 3 bits, right? Now the most significant bit, this W, I am giving as the enable input. So what I am doing is, whenever this W is 0, see, I will be activating decoder 1. So this is a 3/8 decoder 1 and this is a 3/8 decoder 2, right? So what I am doing is I have to activate, because it is an active high circuit, hope you know. So by default it's active high. So whenever I am giving a high or 1 to this enable input, this circuit will be activated. So actually I am giving a 0, but I am negating it, right? So this, whenever I am giving W equal to 0, this negation will take 1 and that 1 will activate the first one. So that the output is now, for this set, the output is like D0 to D7. So I have to activate any one of these 8 pins, output pins, accordingly, whether it is 0 0 0 or 1 1 1, like that. Okay, so that you can do it, right? So whenever the W bit is 0, you will activate the first decoder and that will output you D0 to D7 bit. Now similarly, whenever this W is equal to 1, what will happen? This will be deactivated, because this negation will give you 0. So that this first decoder will be deactivated, right? So that is not going to work at all. So D0 to D7 pins are not going to be enabled, right? Instead, it will activate the second 3/8 decoder, and as a result, any of the output line from D8 to D15 will be activated based on this X, Y, Z. Suppose I am giving something like this, as the W is 1, this second decoder will be activated, first will be deactivated, and now it will see what is this X, Y, Z. It is 1 1 1, and it will this D8 is actually corresponds to 0, like that, for a 3/8 decoder. Similarly, this 7 corresponds to D15. So as I am getting 1 1 1, this 7 will be activated. On the background, it corresponds to D15 for my 4/16 decoder. Hope the idea is clear. It's very simple construction. Let me remove these extra steps. Yeah, what I want to tell you is like this is for D0 to D7, and here this corresponds to, for the 3/8 decoder, this also D0 to D7 only actually. So inside the circuit it is 0 2 0 1 2 3 etc 7 only, but the output I am assuming for what? the first output of this second decoder I am assuming for D8 to D15. So like that it will vary. So this is an important understanding. So how to construct it with a bigger size decoder like a 4 by 16 using a 3 by 8 decoder. Now you can think by yourself how to construct maybe a say you can try like this, how to construct this 4 by 16 decoder itself using a smaller, very smaller size decoder like a 2 by 4 decoder. So you can think of it, right? So I may help you. So maybe you need more, right? Yeah, or how to construct a 5 by 32 decoder using 4 by 16 decoder. So that is very straightforward, just like you use two of them. Now I am asking you like the construction of the same. So let me write it. Yeah. So the question I am trying to give you is how many 2 by 4. So we are taking some more smaller decoders are required to construct a 4 by 16 decoder. So it's not looking much easy, but you have to work out, right? So simply you can see that here I need 16 output, but I am having is just 4 outputs. Definitely 4 decoders are needed, so they can together make the 16 output. But the thing is that 4 enough? Okay, you just work out, you will understand, right? What is the difficulty we are having? Accordingly, we may be we have to slightly modify the idea. So once you understand that, any bigger decoder you can construct using a smaller size, right? So that is what I want. So I am giving it as a homework. You can try at your home. We may see in the class lectures, or maybe I prepare some other video if time allows. Okay, so right now I'm trying to finish the contents. Yeah, that about it. Trying to finish the important contents first. Yeah. So the implementation of a full adder with the decoder. Okay, so that is something another concept which we are interested. See, decoder, the primary purpose, I have some coded information, the CPU examples, everything I told you. So whenever the CPU is getting, you converted your program, say, into some binary image by compiling and assembling, and when that binary image, CPU will take instruction one by one, it will try to execute, right? So when CPU is taking something, it is in the form of zeros and ones, and it should know till what is the opcode. So that is up to the designer level. So those things will be known to CPU. Accordingly, only that chip will be designed. So this many bits are for opcode, and then these are all for addressing mode and operands, like that we know, right? And accordingly, once you separate those many bits, so this many are for opcode. Now you should know what opcode is it. Like if it is addition, the adder circuit is to be enabled. If it is subtraction, accordingly maybe it's adder itself used as subtractor or something different. Multiplication accordingly. So that is what is happening. So each of the output line is now will be connected to different circuit like adder, subtractor, etc. So based on what kind of opcode I am giving to the circuit. Hope this example is clear. This is something I explained in detail in the previous video. So watch it and come to this. So based on that opcode bits, I have to enable one of the device to perform that operation. So that is my requirements. That is a typical application. Now we are trying to see, can I do something more with the decoder, right? Can I do the implementation of some of the combination circuit that we already studied, say, with the decoder, or anything else. So if we can do one of the circuits like what we are going to see, you can implement anything. So just understand the idea. So that idea you use for the design of any combination circuit. Okay, like, so here we are going to see how to implement the full adder circuit with the decoder. And you know what is full adder. So again, I am not going to repeat what is full adder. So please watch the video on full adder and understand this truth table. So for the time being, what we need is, this is a full adder truth table. So this is something for your understanding. I taken it from the full adder PPT. See, you can see that when you are applying 3 inputs, because full adder means what are all the inputs to the circuit? Tell me. The actual 2 bits, so it's a bitwise adder, right? So the 2 bits which you want to add, right? And also, what is your reset? The carry from the previous addition. So you are in effect you are taking 3 bits. So 2 bits is what you have to add currently, and 1 bit is coming from the previous bit addition, right? So everything you know already, right? So this is your full adder circuit, and the output of the full adder is a sum bit and a carry bit. So there will be a sum. When you are trying to add 3 bits, you will get a sum and a carry. And you know, these are all the 8 different ways the input can come. The number to be added are 0 0, and the carry is also 0. And here I have to add 2 1, and the carry bit is also 1. So this is something that gives you the maximum sum and carry, right? So accordingly, tell me what is the sum and carry. You know, when you add 0 0, there is sum bit is 0, carry is also 0. So like that, let's take random. The last combination, you know, when you are trying to add this 1 and 1 1 1, you know, 1 plus 1 plus 1, simply saying it's 3, binary it is 1 1, right? So that 1 is the sum bit, and another one will be produced as a carry. So that will be taken by the full adder next to it. So like that, the addition process will generalize in a ripple carry adder. So we are just seeing the basic construction of a full adder circuit, a single full adder circuit which can add 3 bits. Okay, so that about it. Now you know, so here what is this? This corresponds to the, I mean, weightage. This is a least significant bit. That is what is meant by 2 power 0. Because when you write something, I mean, suppose I am telling you this is the input, like x is this, y is and z is this, and you know, correspondingly d5 will be, sorry, this is z, d5 will be activated, right? Okay, because this 101 corresponds to d5. Now tell me how you are getting this 5. So you are converting it into decimal, right? So this corresponds to 2 power 0, and this corresponds to 2 power 1, this corresponds to 2 power 2. And the number will be like 1 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 power 2. So 4 plus 1, you are getting 5. So the weightage is actually represented like this. So 20 means the least significant bit is to be applied here. The most significant bit is to be applied here. So that is the meaning. So inside the decoder, so the pins will be having certain designation like that. Accordingly, you have to give your input. Okay. Now for this kind of a decoder, 3 inputs are coming, and there will be some 0 to 7, that is 8 outputs, right? So 8 outputs will be there. Actually, you can now understand one thing. Each decoder output, okay, is actually corresponds to a min term, right? Again, min term, something we already discussed in our module 2 in detail. Okay, if you are not able to follow the term, please watch it and come back. So I assume that you are in the flow. So like that, I am discussing the terms that we discussed already. Sorry. So I was trying to take this implementation. See. So whenever the input is something like this, see, these are all right. The output of the decoder, like D0 is this, right? So this is your min term 0, hope you remember, and this is your min term 1, and this is your min term 7, right? So each output of the decoder is actually our min term in the function realization, right? Because if you are looking at the truth table, why it is so? The D0 is activated only in one case, that is when x, y, z all are simultaneously 0. So when all are simultaneously 0, the corresponding min term is like x bar, y bar, z bar. So that is what is your D0. So accordingly implemented the circuit. So each output of the decoder is actually giving you the min term, right? So now you can go for the design of any combination circuit, right? So in this case, see, it's very easy, because how can I implement carry bit? We already have the expression for the sum and carry. Hope you remember the sum is something like x XOR y XOR z, something we derived already. Using XOR gate, you can realize using K-map and all, using that simplification procedure, we come up with this. And similarly, carry was something I remember like xy plus, we saw multiple expression for carry. This is one of the expression we saw. Right, so you can implement that way. So now we are trying to implement the same circuit in a different way, that is using decoder, right? So when you are trying to implement it using decoder, the observation is very simple. These are all my min terms, like min term 0, min term 1, min term 2, min term 3, min term 4, min term 5, 6 and 7. And now each of this min term is actually the output of the decoder, right? This min term 0 is actually corresponds to the decoder output to 0. This one corresponds to decoder output 1. Similarly, etc. This one corresponds to decoder output 7. So the decoder outputs are available here, D0 to D7, right? So now what is the thing? This is just you have to take the output and use a OR gate, because this carry expression is now what? This carry expression is now This carry is nothing but, tell me what is your carry? Summation of, I'm not taking from here, I'm taking from this table. Okay, summation of, this is the minterm, I mean this 3, right? 3 is activated, right? Minterm 3 is activated. Similarly, minterm, this is 5. Minterm 5 is there, minterm 6 is there, and 7 is there. All other minterms are 0. So they are not coming into carry, right? So in any of these case, this carry bit will be 1. So that is a meaning. So carry bit, another expression for it is like M3, minterm 3 or minterm 5 or minterm 6 or minterm 7. So you use a OR gate for 4-bit OR gate. This plus 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 means OR operation, right? And for that OR gate, so simply use a OR gate. So this is the OR gate you are using, and for that OR gate you apply M3, M5, M6 and M7. So that is what is happening. So this is your, so you can see that this is your M3, right? And similarly this next, this is your M5, and this is your M6, and this is your M7. All of them you are applying to an OR gate, a 4 input OR gate, and that is going to give you the carry bit. Fine. Similarly, what about the sum bit? So if you are looking at the sum bit, it is giving you a 1 in case like M1 it is 1, M2 it is 1, M4 it is 1, and M7 it is 1. So this sum bit will be something like a summation of these things, that is either M1 or M2 or M4 or M7, right? So accordingly you just take this. So from this you all these things are available ready made now, right? So M1 is coming like this, this is your M2, and this is your M4. You can see this is from where M4 is coming, and this is your M7, right? So from the last one I am taking, and that is your sum bit, right? So this is a way you can implement this full adder circuit. Not only full adder circuit, take any combination circuit, you will have a final SOP or POS expression like this. Okay, SOP only, sum of product term only we are getting as output of the decoder. But you know, you can modify this decoder and you can try to get the sum term also, but that is somewhat more complex. Okay, for the time being, this much understanding is enough. Okay, so what I am trying to say, any function you take, like you can express that function using some min-term expression, right? Like some sum of product expression, sum of min-term expression. Now just take which are all the min-term activate and use some OR gate, and you will get. So you using decoder and OR gate, you can implement any function. Okay, so how many outputs are there? Accordingly, that many OR gates you have to use. If you just have to implement a single function, a single OR gate is enough, just to feed all the min-terms as input to it. Hope the construction is clear, right? So just try to implement some other circuit also using this decoder, like this by the many converter circuits we saw, like, right? So many combination circuits we saw. So try to implement them also using decoder. Yeah. Thanks for watching.